what we do in the virtualization space at Red Hat. We started with operating system level virtualization solutions a while ago, and first we started with Xen, and we were shipping Xen as our own virtualization solution in RHEL 5. At some point, we realized that there is a better solution on the market, and with the acquisition of Kubernetes, we switched to KVM. And now we do lots of cool stuff in KVM world. We support it for different architectures. We support it for data center and cloud solutions for many customers. And we truly believe that it's the best technology out there, and moreover, it's open source. At the same time, we truly believe in a hybrid world, which is around us. And our customers want to run RHEL in all sorts of environments which are out there. And of course, they run RHEL on RHEL, and they run it on KVM, they run on OpenStack and REV. At the same time, they run RHEL instances on public, private clouds, and all sorts of different virtualization solutions which are out there. Namely, they run them on AWS, and at the same time, of course, they want to run them on Microsoft solutions. And Azure is the second biggest cloud provider in the world nowadays, and of course, they want to run there. And as you might probably heard, we had a big partnership announcement at the end of last year, and now we officially support RHEL on Azure. We were supporting RHEL on Hyper-V before, but now we officially support it even on Azure. So, what is Microsoft Hyper-V? Microsoft Hyper-V is Microsoft's virtualization solution, and it was first introduced in Windows 2008. It's the core of their Azure cloud. The Azure cloud is, as I said, the second biggest cloud in the world, and it actually runs Hyper-V. So Hyper-V is a type 1 hypervisor, which means that it runs on bare hardware. And it's not like KVM when you have a model and you run something inside your operating system as a process. With type 1 hypervisors, you run hypervisor on bare hardware, and then you run your management operating system just as a guest for this hypervisor. In Hyper-V, they are called partitions. And this first guest is called root partition. It's similar to DOM0 in Xen. Hyper-V requires hardware virtualization, but all modern x86 processors support that. And currently, it's able to emulate two different platforms. First is so-called Generation 1 VM, and it is a legacy platform with BIOS and all sorts of emulated devices, including I/O. And you can actually run an operating system which doesn't know anything about Hyper-V there. It's going to be not super fast, but you can run it. At the same time, since Windows 2012, it supports so-called Generation 2 VM. Generation 2 VM is an UEFI system, and it doesn't have emulated devices. So to run something there, this something should be aware of the fact that it is running on top of Hyper-V. It should support Hyper-V specific devices. So yes, how it's done. So Hyper-V emulates x86 system, and as it emulates a standard platform, at the same time it provides us with some so-called enlightened passes and special paravirtual services. As I said, for input-output, you have emulated passes for Generation 1, and you don't have them for Generation 2. So these enlightened I/O passes are mandatory for Generation 2 VM. It also has a set of paravirtual services, such as heartbeat, so your host is aware of the fact that your guest is still running. It has utility drivers, and I'll tell more about them later. It has special services for timekeeping and synchronization, and guests are able to report crashes to the host. So, Hyper-V and Linux. So, of course, Microsoft was interested in running not only Windows in Hyper-V. So they started developing their drivers for Linux, and at the same time they released Hyper-V at 2008. And in 2009, these drivers were added to staging. At that time, it was mostly done by Novell. In 2011, these drivers left staging, and now they're part of a normal Linux driver set. These drivers are present by default in all currently present Linux distributions on the market, and they're completely open source and GPL licensed, so there are no legal issues with them. And as you can see, like currently on Azure, 25% of all VMs run Linux. I got this data from Microsoft, so we should trust them. It should be true. Yeah. So as you can see, that Linux is important for them. So it's not a tiny portion of their business. So who develops them? Of course, this effort is mainly driven by Microsoft themselves, because they're interested in Linux working as a good guest on Hyper-V. At the same time, as you can see, community involvement in the development process is growing. And last year, only half of all commits came from Microsoft. The other half came from community, and namely, like 1/3 of all commits in Hyper-V space came from Red Hat. So we're doing something there. So which drivers do we have in kernel? We have first two is storage driver and network drivers. And these two are crucially important for performance. They're performance critical paths, because that's actually what you do with your VMs. You use some storages and you use some networking, and you want it to be fast. Other drivers are not that performance critical, but they also exist. These mainly are like frame buffer device, so you can draw something on your screen. You have keyboard, and actually the funny thing is that in generation 2 VM, this driver is mandatory. Unless you have it, you won't be able to type anything in your VM. So don't forget to put it in your RAM drive if you want to debug something. It has emulated mouse. It has ballooning and memory hot plug driver, which is very specific to Hyper-V, and I will tell you about this particular driver later. And it also has utility drivers. So, about storage driver. As I said, it's really crucial for high performance. It supports all types of storages with a single driver. So you can connect both SCSI, IDE, or fiber channel devices to Linux through this driver. You don't need different drivers for that. It's SPC3 compliant since Windows 2016, which is not yet released, but we expect it to be released later this year. Before that, it wasn't claiming this compliance, but it was implementing SPC3 features, such as block discard. This driver supports multi-queue because it's a high-performance driver, actually. NetVSC driver. So again, crucial for high performance. Supports multi-queue and scaling on both transmit and receive passes. With on the receive pass, they call it like virtual receive side scaling, and it actually means that your host determines some conditions when it needs to start scaling incoming packets. And it starts pushing these packets to different queues on your guest. And for the transmit path, they call it virtual multi-queue, which is also host-driven, so it can be dynamic or static. With static multi-queue, you just get a number of queues up front, and you can use all of them to send your packets. With dynamic multi-queue, host waits till your guest really needs to scale. And at that point, it actually measures your CPU load and network load. And at some point, it sends you a signal that you need to use more queues. And your driver starts scaling in Linux. As it's a network driver for Windows, we need to decorate each packet with RND's header, which is very similar to some wireless cards which were out there a while back and which had only Windows support. And for someone who is familiar with network stack in a Linux kernel, there is no NAPI support for the driver, so we can't we can, but we still didn't implement the active pooling mode. And I hope that it's going to be implemented earlier or later. So now, Microsoft encouraged me to show you these performance numbers. So again, data is from them. We should trust them. They're on the dark side. They have cookies. So here you can see performance data for the NetVSC driver on a single Hyper-V host. Measurements were done on a single NUMA node 8 CPU system. And I think, this data is from the transmit path. So they were measuring it with like iPerf style test. And as you can see, Microsoft claims that on some connections, like less than 1,000 connections, Linux driver, like on 64 and 256, Linux driver performs better than Windows on Hyper-V. So for some connection numbers, the situation is slightly different, but still the difference is not really big. So we are on par with Windows drivers for Hyper-V. For Azure. For Azure, we are, for some reason, performing slightly worse. But again, the difference is not that, and I forgot to tell you that 40 gigabit per second network adapter was used for the test, and we did like 31 something gigabits per second for the guest, which is pretty okay. These numbers are from these PV drivers, so no device pass-through was used there. So it's not SRIV, it's pure PV pass. On Azure, for some reason, slightly worse, but maybe it depends on like how Azure hosts are optimized. And in this particular instance type, they had 2 NUMA nodes and 32 vCPUs total. And we did well. So I already pronounced utility drivers several times. And what are these utility drivers about? So we have a number of drivers which are not visible for the user. And these are mainly like clock sources and clock events, because for virtual machines, it's better to use paravirtual paths for these devices. We have time synchronization, so when our guest starts, it receives time from its host, and it can adjust its own time accordingly. It also receives this synchronization when we migrate guests. So when we migrate it to the other host, we can get a time counter from the host. We have heartbeat, as I told you. We also have special to Hyper-V devices. and which are paired with user space daemons. And all the source code is in Linux kernel, including these daemons in tools subdirectory. We have 3 utility drivers. First one is key value pair. And actually, it's just a simple key value server. So you can, from the host side, you can store some value on your guest, and you can retrieve the value. But it wouldn't be that interesting unless it was used for network settings. And using this key value pair daemon, you can actually get your network settings from your guests, and you can set network settings to your guests, like adjust their DNS server. We have second daemon, which is called VSS, and it actually comes from like virtual shadow storage, or what was the name for it from Windows. We don't have such things in Linux, but we needed to do consistent backups. So when you backup your guest and you do it live, you want to make your data consistent. And to do that, you need to freeze your file systems before you start doing the backup and actually get the snapshot, because when you run on Windows, your storage can be snapshotted. So Windows does the snapshot for you, and you can like saw them and continue using them. For this purpose, we have a special driver and a special daemon in Linux. There is also an file copy daemon, which can be used to copy files to guests without network involvement. Everything happens through this host-guest protocol, which I will describe you later. Memory balloon. As I told you, this ballooning mechanism is specific to Hyper-V. So what we have, as a customer, you may want to assign more memory to your guests on your host than you actually have. You do this under an assumption that not all memory is going to be used at once. So guests will scale, and they will adjust their memory needs accordingly. And for that purpose, we report our memory pressure, like how much memory is used in the guest every second. Yeah. And we just send these reports every second to the host. And the host, Hyper-V host, can decide whether we need to balloon up or balloon down. Balloon up means that we are giving away some memory. We are actually allocating some memory pages which we are not going to use. And we report their frame numbers to the host. Once host receives these frame numbers, it can actually detach physical pages from these frame numbers and assign them to some other guest. And at that point, we cannot use these pages. Once we try to access these pages, we get general protection fault. So at some point, we may want to get our memory back. There is no direct way to get this memory back. We can just report higher memory pressure to the host. And we expect our host to return us our memory. Host comes to us with these frames and gives us back. At that time, in Linux, we can freeze these pages and start using them as normal memory. The same driver is being used for memory hot plug. Before Windows 2016, it was only possible with so-called dynamic memory, which was a bit slow. What's the real implementation of the dynamic memory, we don't really know. We never saw Hyper-V sources. But since Windows 2016, you can basically add memory to your guests anytime. And this will arrive. We have some weird issues with that in Linux, that in Linux, our memory hot plug granularity for x86 is 128 megs. And in Windows, it's 2 megs. So there is a special handling in our driver for that. Timekeeping. As I told you that in virtual machines, we'd rather use PV passes to get time. So what do we have? We can still use TSC, just like our DTSC instruction. But in Hyper-V specification, it's said that it's not stable. So you can get like huge jumps in TSC value. It can actually jump back. So it's not a good time source. So there are two additional time sources. First is so-called Hyper-V clock source, which is really simple, but it's slow. There is a special MSR from which you can read this time. Why is it slow? Because every time you read from this MSR, it actually means you are exiting to the hypervisor. Hypervisor traps you, hypervisor puts some value for you, and you get back. Good, but slow. There is a different clock source which is called TSC page. And it's actually a shared memory page between you as a guest and the hypervisor. And there is a special protocol how to get time value from this page. You just read some sequence number, then you read something on the page, then you do some calculations, and then you check the sequence number to see that it hasn't changed since you accessed it for the first time, because if it changed, it means that you need to read from the beginning, otherwise your host was updating time at the same time. It's super fast because there is no exit to the hypervisor. You're just reading from memory. We have a bunch of Hyper-V drivers in development. It's like, again, the effort is mostly driven by Microsoft. There are 3 drivers I am aware of. First is Hyper-V socket, and it's actually similar to what we have for VMware, which is named vSoc. And it is a way for 2 applications on your host and on the guest, or on 2 different guests, to communicate to each other without real network. So they will communicate through this host-guest protocol, which is named VMBus in Hyper-V. The second driver is Pci Pass Through, which is designed for some obvious purposes, to pass through a PCI device to your guest. There is no PCI Pass Through at this time. And the last one is RDMA, for a very specific, like for one Mellanox card, they are able to do this RDMA in the guest. And they have a special so-called front-end driver for this Mellanox card, which is in your host, so you can do direct RDMA from your guest. I expect they'll be upstreaming this driver later this year. It's actually open source now. You can see its sources on GitHub, but they never put it to kernel, so we at Red Hat don't support it now. We are waiting for them to start upstreaming it to Linux kernel. So I promised deep dive when I submitted this talk, so now start the deep dive. So how all these drivers work? First, why do we need these drivers? Why can't we use emulated devices for everything? Well, emulated devices would emulate hardware protocols. And these hardware protocols were never designed to be used by host-guest communications. So there is no way we can make them super fast. All other virtualization solutions out there have similar PV drivers, like KVM has virt.io, then has these front-end, back-end pairs, and there are PV devices for VMware. Some devices we have, they just don't have hardware counterparts. So there is nothing to emulate, like this memory ballooning device. As I told you, that there is nothing similar in hardware which can balloon your memory. And we have these Enlightened drivers, Microsoft name, Enlightened. They're from the other side of the course. Yeah. These drivers are implementing so-called VMBus protocol. And VMBus is actually a set of things which you're supposed to implement to interact with your host. And it's based on the concept of channels. Channel is like a single entity for communication. They're bound to particular vCPUs, And you can have one or more channels for each devices. We have a way to transmit data, and ring buffers are being used for that. But as we are using like ring buffers, we'll also have to have a way of signaling both ways. So our host should be able to somehow signal the guest that something is going on, and our guest should be somehow able to signal the host that there is something needs handling from the host side. So how do we signal something to our host when we're in the guest? The concept is called hypercalls, and it's super simple. You allocate a simple memory page, and you create like a virtual mapping for it, and then you put the physical address to some MSR for the host. Then you treat it as a function. So I have some function there. So once you want to perform hypercall, you put something like input, output, and like hypercall ID to your register, and you just call the page, thinking that, oh, there is a function there. Hypervisor traps you there, performs the function you asked for, and returns back. And you can look at your output, like usually you put some address there, and hypervisor will write something there. So how does host signal something? There are two concepts in Hyper-V. They call messages and events. Messages are being used for non-performance critical communications, and they usually mean that something is going on with the channel. Like we want to open a new channel, we want to close a channel, we want to like restart the whole communication, unload everything. And it's actually like a single page per vCPU where there is actual data. When you receive an interrupt, like physical interrupt from your host, you're supposed to look at the page, and if there is some data there, you get a message from the hypervisor. But this message is limited to 200-something bytes, and as you understand, you can't make any performance-critical communication based on messages, because you'll be just delivering one message per call, and you'll need to have an interrupt for each of them. So it's going to be dead slow. We have events. Event is a different page per CPU. And when we receive this interrupt from the host, it's actually the same interrupt which signals messages. We are supposed to check this page, and this page has an indication which channels have data to process. There is like an index there, so it's kind of fast. We don't scan the whole page to see all the bits. And we get all the channels which require processing. We go to these channels, and we process data. Where is the data? The data is in ring buffer. So ring buffers, very simple concept, where you have some memory space. Actually, there is nothing like circular data structure in your memory, so you use some amount of memory, and then it like wraps around. So you have like two positions, like reader position, writer position, and the data between them is unprocessed data. So writer writes, reader reads. Nobody blocks the counterpart. So for each Hyper-V channel, you have two rings, two ring buffers. One for sending data, and the other one for receiving data. And these rings can be really different in size. So as you can see, like for the network driver, we use like 128 pages. For storage driver, we have 256 pages. For some non-performance critical devices, we use much smaller rings. So we need to somehow signal that there is data. So on the receive ring, this is not symmetrical. So on the receive ring, we receive this physical hardware interrupt when there is data. So we check this event page, figure out like which channel it has, go there, and we are supposed to read all the data which is on the channel. Because if we have like more than one packet there, we won't receive new interrupts for the remaining. So we need to read them all. So at the same time, like if the whole RIN was filled with data, we need to signal the host back, okay, we processed the data, there is some space there, you can continue. On the transmit RIN, where we put some data for the host, we have two guarantees from the host. That first, once the host starts reading from this RIN, it will read all data which is on the RIN. Second guarantee is that it will indicate that the reading is ongoing. So with these two guarantees, we can only signal our host because like we signal with hypercall. Hypercalls are expensive. So we are trying to make as less hypercalls as possible. So we only signal when our RIN goes from empty state to non-empty state. In all other cases, we either already signaled the host and it will process the data, or the host is actually reading the data, so we don't need to signal. That was it, actually. You probably have some questions for me. Please.
You mentioned at the beginning the crash reporting. May you explain a bit? Because some months ago I had the issue while rebooting a Linux system within Hyper-V, it simply crashed while rebooting, and had a lot of fun with GSS until we were able to figure out something.
Yes. So there are special MSRs which Hyper-V emulates, where the guest is able to report that it actually crashed. There is not that much data which you can put there, but you can put there like your instruction pointer and some set of your registers, CPU registers. Why is it useful? It's useful because if you have a huge cluster of Hyper-V hosts and you have crashes, you want to be able to identify fast if you have identical crashes or different crashes. And you can do that just from like looking at this instruction pointer. If they're all crashing at the same instruction pointer, that this is probably the same crash all over the cluster. And you can see these events in Windows event log. So once you write to this MSR, you actually do, the protocol is like that. You put like your instruction pointer AX, BX, CX, DX, and then you write to this control MSR, which means report the event to the Windows host. Nothing happens to your guest after that, so you can actually report several crashes. It won't like kill your guest or something like that. But then looking at your Windows event logs, you can see that your guest actually crashed, that this specific 18,590 event, and it tells you where your guest crashed. So you can just take your like Linux kernel image, do adder to a line, and you will see where your kernel crashed. Even if you didn't get like kdump or you have no console output, like nothing. Just out of this data you can get something sometimes. Sometimes not. Sometimes it's just some random instruction pointer and there is nothing like that in your kernel.
Is there a recent feature or is there a recent feature or is it something that should exist already?
It is an existent feature. Yeah, the question was, sorry. The question was if this feature exists or in development. It is an existent feature in Hyper-V and it is an existent feature in Linux kernel since last year. I think like the beginning of last year it was implemented upstream. Please.
About the utility values you mentioned in the Linux sources, like we want to do the VSS freeze or the file transfer behavior. How are they that we have to explicitly start them in the guest, have them work, and can you filter what they can do, or like for example not changing some of the network parameters?
Actually, there is no control for them. So you either start them or not. There are two parts in Linux. First is kernel driver. Second is this user space part. And they communicate through character device nowadays. So it actually does what it's designed to do. Network driver, it calls scripts. So you can actually alter them, like set IP address, and it is a script. You can put whatever you want there, or just like.
Follow up. What happens if the hypervisor want to use those things and the user space is not running? And is it the same between like Azure and standalone hypervisor?
In Azure, yeah, you are not able to access the host, so I'm not sure what's going to happen, but there are probably some like management engine around that. On Hyper-V, you'll just get an error. Like you can use PowerShell, and with the PowerShell there is a command like assign this IP to this VM. If the daemon is not running in your Linux guest, you will just get an error, like or a timeout. If like there's no module, nothing. More questions? Please.
Just two. When you are talking about this shadow copy in Linux, can we use, for example, LVM snapshotting for that purposes on Linux?
We don't actually need to, because everything is going to happen on Windows side. If our volume is on Windows, and it actually is, that Windows can do real VSS snapshots for like the whole file system with the volume.
Okay.
So the only thing we actually need from Linux is to make it consistent. So we do freeze for all file systems, do the snapshot, and then we thaw them. So it actually takes like a second or two. So your guest is not blocked for like minutes when you do the backup.
Okay. And the second question, maybe it's a stupid one. Have you some comparison between, for example, KVM running Linux as West and Hyper-V, if in matter of stability, of speed, and so on?
I think like there are way too many comparisons like that. So for different workloads, you'll get like different results, and it's not like, oh, this particular solution is better. At Red Hat, we are like trying to do our best to make all these workloads work as good as possible. Like, so we are not like slowing down one workload just to make the other look better. Like we could. More questions?
Thank you.
Thank you.